So today we're going to take a look at a more complex way to take integrals, something called integration by parts. One thing you've seen in Calc 1 is that you're not able to take too many integrals. A lot of the integrals we can do are fairly special problems that just happen to work out. A lot of the u substitutions that we have done only work in very specific cases. It's almost a coincidence that they work sometimes. There's a lot of equations that you just can't take an integral of yet. Like if I, for example, take the integral of x squared times e to the x dx. We can't do that one right now. You could try to make a u substitution somehow, but it wouldn't work. Coincidentally, if I change that to the integral of x e to the x squared dx, now the u substitution actually does work. You can make u equal to x squared, du is 2x, and you can see how the u will replace there, and with a little bit of manipulation the du will replace that x there, and that one works. But the very similar problem over here, if you want to try the u substitution yourself, it does not work in that case. You're still left with a 2, I think, in the exponent. And you can't do anything like that because there's no chain rule for integration and there's no product rule for integration. We have those rules for taking the derivative, but not for integrals. So fairly simple problems like this are so far eluding us. Integration by parts allows you to do a little bit more integration. And where it comes from is the product rule for derivatives. And so let's take a look at the product rule for derivatives. Let's say we want to take the derivative with respect to x of some function u times some function v. Alright, so those are two functions that are multiplying by each other. And so if we take the derivative of them, we have to use the product rule. So the derivative of the first is simply u prime times the second plus the derivative of the second times the first. So there we have just a basic rewrite of the product rule. We're not interested in derivatives, however. We are interested in the opposite of derivatives, integrals. And so what we're going to do here is we're going to take the integral of both sides. So we're going to take the integral of the derivative on the left and the integral on the right side. Now we got the addition. There is an addition rule for integrals, and so we can place another integral sign right there. Now, one thing we learned last year was an integral is the opposite or the inverse of the derivative. So the integral and the derivative essentially cancel each other out. So we're going to be left with u times v is equal to the integral of, and I might switch a few of these around, v u prime, all I did was switch those around, not too big a deal, plus the integral of u times v prime. Again, all I did was switch those around, no biggie there. Alright, and then what we're going to do is we're going to isolate this integral here. So that means I have to subtract the other integral. Alright, so if we do it to one side, you got to subtract it from the other side. And so you're left with u times v minus the integral of v times u prime equals the integral of u times v prime. I can see how this doesn't look like it's helping us at all, but it will here in a second. I'm going to rewrite this v prime, the derivative of v, I'm going to rewrite as the derivative of v. U prime, I'm going to rewrite as the derivative of u. Alright? And I'm going to put this term first, because that is actually what we're interested in. So the integral of u times dv is equal to u times v minus the integral of v times du. And here's what we're hoping. We're hoping that when we find a problem, we'll find an integral that looks like this that we cannot do. Okay? But then we're hoping when we manipulate things and we find this integral, we can do it. So that once we break up u and we break up dv, that the integral here is something we can actually do, when the one over here is one that we cannot do. So I'm guessing that still doesn't make a whole lot of sense. So I'm going to give us an example here. Alright, let's do some green. So we're going to take the integral of x to the fourth times the natural log of x dx. Which, we can't do this. No u substitution is going to help. If I think about trying to make this the u, you're going to have a 4x to the third, and there is no 4x to the third over here anywhere. So what we want to do is use integration by parts. And so we've got to first figure out what is u going to be. And once we figure out what u is, we can figure out the derivative of u. And then we have to figure out what is dv. And then we can figure out what v is going to be. We've got all those four parts. As you can see, we've got 1, 2, and then 3 and 4 parts. U, dv, v, and du. All those 4 parts. So first off, in our original integral, we have to pick one side to be u and one side to be dv. So one of these is going to be u and one of these is going to be dv. Okay? And so in this case, I'm going to pick u to be natural log of x. I'll tell you why in a second. And dv is going to be x to the fourth. Okay? The reason why I choose those two like that is because if I want to go from u to du, I have to take the derivative. Natural log of x is an easy derivative. It's 1 over x. Okay? If it would, now on the other side, I have dv, and if I want to go from dv back to v, from the derivative back to the original, it's going backwards, I have to take the integral. The integral of x to the fourth is easy. It's 1/5 x to the fifth. Okay? If I had accidentally switched those, if natural log was over here, I would have to take the integral of natural log, and we don't know that yet. So that would not have been an option. So when you're picking them, your u, you're going to have to take the derivative of u. So you want to pick which one here is easy to take the derivative. And the one you pick for dv, you're going to have to take the integral. So you want to pick the one that's easy to integrate. And then you hope it works out. So I might as well write this up here at the top, up here. So the integral of u times dv is going to equal u times v. So I'm going to take u and multiply by v. Natural log of x times 1/5 x to the 5th minus the integral of v du. So I'm going to take v, which is 1/5 x to the 5th, times du, which was 1/x. And I'm going to rewrite the first term here. I'm going to put the 1/5 x to the 5th in front. I think it looks a little nicer. Minus, now what happens to my integral here? A 1/x and an x to the 5th, well, that's going to cancel out a little bit, isn't it? That's going to be 1/5 x to the 4th dx. So that actually accomplished what I wanted. We took an integral that we could not do. This integral over here we could not do. And by doing these substitutions, we now have an integral here that's very easy to do. Very, very easy. Let me finish that off. So we have 1/5 x to the 5th natural log of x minus, let's see, the 4, turn it into a 5 and bring it down. That's going to be 1/25 times x to the 5th plus c. And then I'm going to pull out, let's see, we have two terms here. This one has an x to the 5th and that one has an x to the 5th. So we can pull out an x to the 5th. They also have a 1/5 in common, don't they? So pull that out. You're left with natural log of x minus, let's see, that one went away, and 1/25 turns into 1/5 plus c. So there is our integral. That one is a little complicated, but hopefully that shows you how you can take an integral that we cannot do, find these four pieces, and then use the integration by parts formula, which we did sort of prove over here, and take a complicated integral and turn it into something simple that you actually can evaluate. One note, as you go through the book problems, the book does not organize it this way. They switch those letters around. They have all the letters there, but they're in a different order. I like this order because you go U, or U and DV have to go next to each other, and so I like to put them horizontally next to each other. I think they may organize them vertically. Whichever one works better for you, it doesn't matter as long as you have all the parts, and as long as you take the derivative to go from U to du, and as long as you take the integral to go from dv to v, then you can just plug all your pieces into here. But it is a little bit of a puzzle to figure out what goes where. You'll catch on. Good luck.